the slides now. So once again, thank you everyone for being here. This is part of our weekly webinar series for Amigos de Bolsa Chica. And my name is Joana Tavares. I'm a marine scientist. I've been working with phytoplankton since 1998 and going strong. I did a number of things in my career working with phytoplankton and education, and then I decided to go back for a PhD here at UCI in the Earth System Science Department. That's what ESS stands for. I work in the Mackey Lab, which is a lab dedicated to phytoplankton and global biogeochemistry. And our lab studies the effects of climate change on phytoplankton, and our department includes a number of professors dedicated to modeling, to trying to forecast what the future impacts of climate change will be in the ocean and on phytoplankton as well. Okay? Now, this presentation, I should start with a warning. Warning, this presentation might give you nausea, headaches, constipation, and other weird side effects because it includes a lot of technical information, a lot of graphs. But fear not, we're together. If you have any questions, just raise your hand. There's a raise your hand function, or just unmute yourself and say, hey, Joanne, I have a question. And then we'll stop and go over it. Also, don't feel frustrated if there are graphs that are just too complex. They are really complex, even for scientists. I will try to walk you through them, and I'll try to tell you why they're important. But nobody expects you to actually fully understand everything that is there. I just want you to have a visual that you recognize if you see somewhere else. Okay, does that make sense? So just my little warning before we start. Okay, so hold on, I'll go forward here. So just a brief overview of what we're gonna do. We're gonna start by talking a little bit about phytoplankton, which this group here, most of you are already familiar with phytoplankton, but we're gonna go over the definition, some examples, and why they're important. Then we're gonna talk a little bit about climate change. I'm gonna define some terms. We're gonna talk about the causes of climate change and some of the general consequences. And then we're gonna dive into climate change in the ocean, how the two are related, what is happening to the ocean because of climate change. And then we're going to talk about climate change in phytoplankton more specifically, where I'm going to tell you what we've observed in the past few years and what are the expected impacts as we move forward. Most of the predictions are trying to forecast the impacts down to the year 2100. And I'm also going to share some of the results from my department here, which is trying to predict the impacts down to 2300. So. All right, so starting with phytoplankton, you're all really tired of seeing this picture, right? Every presentation I give, I show this picture. I love this picture. This was taken by our friend Peter Bryan. You all know, many of you know Peter Bryan. I was with him on this day that he took this picture. This is a mixed sample of phytoplankton. And I usually call on Judy to name some of the organisms here. Judy, do you want to help us?
Well, there's serration furca, there's protoparadinium. Looks like, oh.
Yeah, I wanna be pointing. So she's talking about serration furca, very good. And, what else?
Protoparadinium.
Protoparadinium. Oh man, my thing is so slow here. Okay, protoparadinium is the round, this one,
yeah,
with the pink
the little
stuff.
Santa Claus guy. Is the one down at the center bottom, is that a Coscina discus?
Yes, it's a Coscina discus.
We don't usually see the cylinder.
Right.
That's wonderful.
Very good. Yes. What about this one? Oh, this one's tricky.
Oh, a diddlum.
Ah, she knows all of them. Look at that. And we have Dinophysis acuminata. So this is, thank you, Judy. This is a very common, mixed sample.
What about Lingulodynium?
Lingulodynium, where?
Isn't there one in there?
There one here. No, I don't see any, but oh yeah, maybe this one. Maybe this guy could be. Good job, Bill. Yeah.
Well, that's what you usually hang on me, isn't it?
That's right. That's a Lingulodynium. And look at you pronouncing it like a pro. Yep. So this is a common sample that you would catch with a plankton net if you go out to the shore near the, you know, the on the beach or a pier. And these are really relative. They're, of course, these are all small. This picture was taken with a microscope. These are phytoplankton. They're not visible to the naked eye. And yet, relative to other organisms of the phytoplankton, these guys are really large compared to other organisms of the phytoplankton that you would find in open ocean. And we're going to talk about this later, okay, about size and what might happen with climate change and the composition of the phytoplankton, the groups that make up your phytoplankton. Because phytoplankton, it's a functional term. We talk about all these microorganisms that are photosynthetic. In the ocean, we talk about them as phytoplankton, but not all of them are the same. Some have different requirements, some like different things. By the way, could anyone tell me the name of one major group of phytoplankton that you see here? Like Coscinodiscus, Ditylium, Pseudonychia, they're all, what kind of phytoplankton are they? Are they diatoms or dinoflagellates? These big guys that make their bodies with silica.
Dinoflagellates.
The silica ones? Bill?
Diatoms.
Diatoms. Thank you, Bill. And then the other ones.
But there's more dinoflagellates than there are diatoms.
Right. Exactly. In this picture, there are more dinoflagellates. But I'm trying to, again, talk about how different phytoplankton will have different requirements. They will make their bodies with different components, different elements. And so they will require different things. And same goes for temperature. Some of them like colder water. Some of them like warmer water. Some of them might have a preference for pH. So that all will come, you know, it will be important later on when we're talking about what to expect in terms of a changing world and these organisms, okay? The really small stuff that you wouldn't see here are what we call the cyanobacteria. So the cyanobacteria can't see with this kind of microscope here because they're so small, but they are the ones that are most abundant in the ocean, especially in open water as you move away from the coast. Why are these guys important? Can someone help me out? Tell me one reason why phytoplankton are important. Anyone?
Oxygen.
Oxygen, they produce oxygen through what process? Somebody else besides Judy. She's dominating here, my plankton.
Photosynthesis.
Photosynthesis, thank you, Sarah. Yes, photosynthesis, they photosynthesize. So they transform CO2, carbon dioxide, into oxygen through photosynthesis. And by doing so, they're also creating organic matter. That's the process that generates the first step of the food webs. So these guys here are the major primary producers in aquatic ecosystems. They're responsible for 50% of the primary production on planet Earth. That means that every other breath you take, you're breathing in oxygen that was created, that was generated by photosynthesis in the ocean, by phytoplankton. And they serve as the, like I said, the food is the basis of the food web, so they'll feed everything else. Okay, are we good? They play important roles in climate control. I'm not going to go too much into the detail. They have other reasons. There are other reasons why these organisms are important, but we're going to keep it simple. We're going to move forward. And if I mention another reason why they're important, you will probably be able to connect back to this here. Okay. Any questions so far? I'm moving on. So now let's talk a little bit about climate change. There are airplanes. Can you guys hear my airplanes here outside? Well, they're not mine, but let's get this here.
Joanna, we lost audio on you. Or
Lost audio?
yeah, when you put your headphones in.
Okay, so let's just drop it. If there's another airplane, I apologize. All right. So who wants to help me out with climate change? What is climate change? Oh, you didn't expect you're gonna have to talk today, huh? You forgot it was me. Come on, somebody, help me out. Climate change, what is it? Why do we care? What's the big deal?
Things are getting warmer.
Things are getting warmer. Yes, planet Earth is getting warmer, right? And the reason why is because we are we humans are causing the intensification of a natural process called the greenhouse effect. So the greenhouse effect is something that is normal to the planet Earth. It's natural to planet Earth. In fact, is what allowed life to evolve as we know it on planet Earth. The main greenhouse gases, would anyone know what the main greenhouse gases are? Name one, quick.
Methane.
Methane is one, yes. Everybody loves methane. Where's the main source of methane on planet Earth right now?
Cows.
Cows farts, cows burps. Everybody loves cows flatulence. No, nobody does love that. But yes, methane comes out from cows, also from just decomposition of organic matter. So like when food waste is actually a huge source of methane, landfills in general. Okay, what's another one besides methane?
Carbon dioxide.
Dioxide, yes. The main source of that?
Fossil fuel burning.
Fossil fuel burning, yes. Of course, there's respiration, but I'm talking about the extra stuff, right? It's fossil fuel burning. Also water vapor, but water vapor is actually part of like this interesting feedback. And then we have other gases like nitrous oxide and other CFCs, other gases that might also play a role in greenhouse effect. So under normal conditions, having these gases in the atmosphere is actually a good thing. It's like I said, it prevents the Earth from freezing completely. If we didn't have those greenhouse gases in the atmosphere, the Earth would actually be, an average temperature for the Earth would be minus 18 Celsius. That would be 0 Fahrenheit. So that would be the average temperature for the whole planet, okay? So these gases, they prevent the loss of heat into the ocean, back into space. The sun radiates light on the planet absorbs that light, converts that into heat. The heat is re-radiated out into space, but it gets trapped by those greenhouse gases. And that we usually talk about that working kind of like a blanket. It's not the perfect analogy, but it helps people understand. So what's happening now is we're putting more and more of these gases into the atmosphere. So we're making the blanket really thick. We are not allowing the heat to escape as it should. And so that heat is accumulating near the surface of the planet. And as you'll see, it's going into the ocean. So that's what causes the greenhouse, the intensification of the greenhouse effect is what's causing climate change. Now, the heat that we're seeing is not distributed evenly around the planet. So some areas of the planet are getting warmer faster than others. And so climate change is a term that that's more appropriate than global warming, because what we're seeing, even though the planet is getting warmer, sometimes the evidence for that is not necessarily just heat. It can be having more snowstorms in some places. It might actually be caused by climate change. Okay, so this is the first very, scary graph that you'll see here. And I thought that was important just to talk a little bit about how do we know this stuff, right? So we know this stuff because we've been measuring the temperature change in recent years. And by recent, I mean like the last 50 to 100 years, we've had the means to measure temperature change in water and in the soil and the surface of the planet. But we also have other proxies that can be used. So those proxies, they include gases trapped in ice. So the scientists, they go and they drill for these ice cores, and they can measure the types and amounts of gases in the ice core, and they can figure out, based on those measurements, they can figure out what the ambient temperature was. You have fossils, you have pollen, you have tree rings, you have all these different ways in which scientists can then create this proxy records, and they combine that with contemporary measurements, and you can actually trace the change in temperature of the planet all the way back to 2,000 years, as you see in this graph here, right? So you can see this is sometimes this is a version of the so-called hockey stick graph, because you see how much the temperature has increased since the Industrial Revolution, right? This is this huge exponential increase in temperature. And these are temperature anomalies, meaning changes of temperature in relation to a baseline or to the average of the data. So the average of the data would be around here. oops, around 0, and then these are deviations from this baseline. All right, so what causes it? We've already kind of alluded to it a little bit. Of course, global population. Do we know how many people are on planet Earth right now? Can anyone shout out? Just make sure you're awake.
7 billion.
7 billion, yes, around 7 billion people. So we're growing, we continue to grow exponentially. So that's one huge, it's putting a lot of impact on the planet. Lifestyles, of course, yes, the way we live our lives, the way we consume, the amount that we consume and what we consume. But also I want to call out your attention to systems, right? So we've built systems based on these things called fossil fuels, and we really got addicted to it. And even though new technology has emerged, new technology that can replace fossil fuels, even though we've known about this whole greenhouse effect intensification and climate change, we've known it for a while, since the 60s. We really have failed at changing these systems. These are not easy changes, obviously. We're talking about changing huge amounts of infrastructure. We're talking about changing, many segments of our shared life as societies. But it's doable. And I think one interesting piece of information here is this one that you see in this graph. So this graph here shows you the top 20 companies. And these 20 companies listed here, many owned by governments, by countries. Many of them are not just necessarily private companies. Some of them are owned by specific country governments. But these 20 companies have an estimated contribution of 35% of all energy-related carbon dioxide and methane worldwide. Okay, so it's not, I'm not trying to say that it's easy to change or to solve this problem, but here you have it. It's not something that is impossible if you can address where it's coming from. So that's my little activism bit here. So going back to more of the science, any questions so far? Remember, you can stop me, right? Okay, so this other graph will show you the change in the amount of CO2 that we're putting in the atmosphere per year. Okay, so this here shows you in 1960, the black line shows you the total for the whole planet. So all of us people of the planet Earth. 1960, we used to put something around, I'm gonna say around between 3 and 4 gigatons of CO2 per year. By the 70s, we were already up here, I don't know, somewhere around 6 gigatons of CO2 per year. 80s, right? Then you go all the way to the hit. Does anyone know what this dip is here? Around 1990, 1991. Anyone remember losing all their money on a crash? Remember that? This here was the 1991 crash. This is when Saddam Hussein invaded Kuwait, and we had like an oil crash right here. And so you can see these emissions trends, they vary with what is happening in our society. If you keep going, how about this one? Around 2007. You guys remember 2007? 2007, 2008, our Great Depression, our most recent Great Depression. So you can see how this is not something that is untangled from our, from our economic ups and downs, from more global markets. Really, this is something that reflects what we as one global society go through. Obviously, now we can take a look at what's happening per country, and you see these are the largest emitters if you divide the emissions per country, and you're going to see that the United States was the leader, was the top emitter for many, many years. And then back around between 2005 and 2010, it got taken down as first place by China. But I will make a claim that some of these emissions here are actually being generated by the manufacturing of goods that get sent out back to the United States. So I'm going to claim that some of these emissions here are not necessarily reflecting the, you know, well-being of the Chinese people, that some of this here has to do with what we import from China and other countries too. This is the European Union in blue, and this is India. Anyone wants to say anything about this graph or about any of this before I move on? No? You guys are awfully quiet. I get scared.
Are those just the top 4, or are those just kind of random selections?
No, these are the top 4. Yes. Yes.
Do you know how this is estimated?
Good question. So these are estimated with a number of different combinations of pieces of data. So some of it is measured. It's actually measured, like they will actually measure the amount of CO2 in the atmosphere in different parts. They will also be taking into consideration production rates. So production by industries that they know exist in those countries. They actually will fix some of the data and try to make sure that what the measurements that they have from the actual atmosphere matches what the expected values are for production rates at different countries. Who asked me that?
Me.
Who? Me? Who? Hold on. Wait, I don't see you.
Oh,
Sarah.
Video back on.
Sarah? Yeah. So Sarah, that's a great question. I can't give you a precise answer, but I know this data is not just one source of measurement. This is a combination of different metrics that they use to reduce the error of the measurement. Good question. I'm gonna look it up, and I'm gonna give you an exact answer on the feedback email.
Thanks.
Thank you for asking a question. So someone is awake. Anyone else? No? Okay. Okay.
Do you know when we started sending our recyclables to China?
Aha, that's a good question too. I don't know, but yeah, I hear you. You wanted something here.
Yeah.
Right.
I'm
So
trying to look that up.
I don't know, but that's a good question. So we are, yeah, and China's not taking our recyclables anymore, which is kind of interesting. So we're still importing goods, but now we don't have what to do with stuff. Okay. So one other really scary, ugly looking graph, but hopefully one that will give us an better understanding of what we're dealing with here. So again, these are anomalies. So these are changes in temperature in relationship to a baseline here, right? And so it goes all the way back to the 1880. So you can see here the process of industrialization and the rise of global markets. So what you see in red means that the temperature has increased in relation to this baseline. Again, you can visualize the dips as being moments in which we're producing less, consuming less, using less fossil fuels. So it's not something that is just disconnected from all the data that we have to make sense of these changes. So this is the temperature change in response to those CO2 emissions that you saw before, right? So one thing is to think about the emissions of the greenhouse gases, and then now this is the consequence. You're actually seeing the change in temperature as a response to the change in greenhouse gases in the atmosphere. Does that make sense? And they match really well, and they also match with what we know what was happening in terms of our societies and economies. All right, but here, what I want to draw your attention to is that the heat that you're seeing here manifested in the form of temperature anomalies, this heat is being generated by the CO2 that I showed you, but there is a lot more heat that those gigatons of CO2 are generating every year in the atmosphere. And a lot of people don't know this, but most of this heat, more than 90% of the heat that these greenhouse gases are trapping in the atmosphere is actually ending up in the ocean. The ocean will be taking up 90% of the warming that we humans have been causing by increasing the amount of CO2 and other greenhouse gases in the atmosphere, okay? 30% of that 90%, so 30% of the heat caused by humans is actually going into the deep parts of the ocean, what we consider to be deep, which is below 700 meters. And we're going to talk more about that in a minute. So I just wanted to make sure that I connected that with this. So if it weren't for this fact that the ocean is taking up so much heat, if it weren't for that, these anomalies, obviously, we would be melting by now. Like, you know, we're talking about a considerable moderation of surface temperatures that is caused by the fact that the ocean takes up all this heat from the atmosphere. Questions about this? Okay, moving on. All right, another scary, ugly looking graph. Remember, you're gonna have the recording and you're gonna have access to the slide. So if you have any questions later and you keep like, you can't sleep because that graph keeps coming back and haunting you and you're like, I don't remember if I could understand this, make sure that you contact me. I'm gonna try to just tell you why this is important. This is important because this is a projection. So everything that I showed you right up until now were things that we have been recording or observing or extrapolating from those proxy records. And now we're going to start talking about projections, what we think is going to happen forward in time, right? So you have all these scientists who are experts in models. They create these mathematical models. These are they're a series of complex equations that take into account all these different variables that control the climate of the planet. And then they try to, they actually not only try, they do succeed at projecting into the future. And what you see here are two sets of projections. So the one in red and orange here is showing you what the scientists predict will happen if we continue emitting at the same rate that we are. So this is what we call business as usual. Sometimes you see that abbreviated as BAU, business as usual, or sometimes you will hear people talking about RCP 8.5, okay? These are all referring to the same thing. It's referring to us humans continue consuming fossil fuels at the same rate that we have been. So if that happens, the scientists then have these models, and what you see here, the shaded area, shows you different results. These are 39 different models. So these are the outcomes of 39 different scientific groups around the planet, around the world. And when they run their models, their results fall within this range here. So this is what we call the uncertainty of those model projections, is the range. Now, so is there uncertainty? Of course there is uncertainty. Science always has uncertainty. In fact, if you ever see a number in science, that means that number has some other number that goes with it, which is called the uncertainty. So this here shows you the uncertainty, but here's the interesting thing. These projections all kind of converge into this zone. So what it tells us is that by the year 2100, all these different 39 different models are telling us that in the best case scenario, in this business as usual, we're going to be seeing an increase of temperature that will be somewhere around 3 degrees Celsius. In the worst case scenario, something just be like around 5 degrees Celsius, and it will fall somewhere in between. You know, if we take the average of those estimates, we're looking at something around 4 degrees Celsius increase, an average. And this is average for the whole surface. That means some places will be much, much hotter than that, and some places will be colder than that. Okay? In blue here, you have the best possible scenario, which is the 2.6. Some will tell you that this is not achievable anymore. I'm one of those people. Okay? So if we can change our ways, hopefully we'll be somewhere in between these lines. So those are the estimates that those modelers are giving us. This is all summarized in this report put out by the International Panel for Climate Change, the IPCC, and they have a report called the AR5 is the latest one. And all the reports, they have like a summary that we call Summary for Policymakers. That's all available online. And if you ever want to see them or want to help understanding them, let me know. I had to pass some courses to call myself a PhD candidate on this stuff. So I want to put it to good use.
Joanna?
Any questions? Yes.
Yes, the lower 32, the number in blue that you were alluding to before, what types of changes would be necessary to meet those goals? Is that the changes that we see in the Paris Climate Accord?
No.
Or what changes would it be? Pre-1990 levels of carbon?
Yeah.
Could you
We're talking. Yeah, I can't. I'm gonna probably not give you the most accurate answer here, but I can tell you that it would mean stopping emitting immediately and developing technology to do carbon capture to reach this number here. The 32 is just the number of model runs. Okay, so 32 indicates the number of models that created this this line and the uncertainty. Okay, but to achieve this here, it would mean not only completely stopping emissions immediately, but also investing on technology to remove carbon from the atmosphere and pump it back into the ground. Okay, so not something that we could even do just by changing our lifestyles or by changing the source of energy that we use.
So you're saying that we would not only have to have zero emissions, but we'd have to have some way to capture the carbon that has already been emitted into the atmosphere, yep. Those 16 gigatons you were talking yep. about earlier. Okay.
Yeah. And that's a great question. I will also, Jen, Amber, can you please keep track of the things that we're going to send on the feedback? I'm pretty sure I can find some really good information about that, because that's a great question, Tom. I can tell you what change would we need to make in order to reach each of these scenarios. I can send that to you.
We'll make note of it.
Thank you. All right. So what about the ocean? How's the ocean dealing with all this? So as I mentioned before, I'm going to start actually with my bullet here below. So I'm a little backwards here. So as I've already mentioned, the 90% of the heat that is being, I said generated, but in reality it's trapped, right? The heat that is being trapped in the atmosphere because of our increased consumption of fossil fuels is going into the ocean, right? Now, that is separate from the carbon that the ocean absorbs. Besides the heat, the ocean is also taking up CO2 directly from the atmosphere. So you drive your car, right? You're driving your car, and your car is releasing all that CO2, right? That CO2 goes into the atmosphere as CO2. It's not trapping any heat yet. It's just there. Well, guess what? 1/4 of that CO2 is going straight into the ocean. It didn't even get a chance to warm the planet up. It went straight into the ocean. Another quarter, the estimate is 1/4 to 1/3, okay? Another quarter goes into soils and forests. They take up about 1/4 of the CO2 emissions. And then the rest remains in the atmosphere, and that's where it becomes a greenhouse effect gas, and that's where it traps heat. Does that make sense? Because this is really confusing to people. There's two things that the ocean is doing for us. It's ameliorating climate change in two different mechanisms, by taking CO2 from the atmosphere and by taking heat that is caused by the CO2 that stayed in the atmosphere. Good? All right. So I want to call your attention to the CO2 that is going into the ocean, the CO2 itself. So about like I said, 1/4 to 1/3 of the CO2 that we've emitted and put in the atmosphere does not stay in the atmosphere, goes into the ocean. That's a problem. It's a huge problem for the ocean because it messes up with the chemistry of the ocean. Now, you guys measure pH, you used to every week when you went to flow, you used to measure pH, right? What's the pH of the seawater in general? It's about what? Does anyone know?
8.
8, yes. So the ocean water, and 7 is neutral. 7 in the pH scale, it's a log scale. In the pH scale, 7 is neutral. Anything above 7, we say that is basic. Anything below 7, we say that is acidic. CO2, when it goes into the ocean, it becomes an acid. And through a series of reactions, this acid will actually mess up the pH of the seawater. So what we're seeing, we're observing, we're measuring, this is not prediction, okay? This is being measured, is that we're seeing the pH of the seawater drop from 8 to a number closer to 7. And that, of course, that's not uniform. Again, it's not all over all the ocean water on the planet. Some places are seeing greater decrease than others. But in fact, what we are seeing are already not only this measurement, but the consequences of that. So what happens is when the ocean becomes more acidic, and that's what these pictures here are showing you. Again, there's a lot of information. I'm not going to walk through all the chemical equations. I can explain them to you if you want me to later, separate, but I don't want to overwhelm everybody. The gist of it is that more CO2, which is in this picture here, more CO2 means that you're going to have fewer carbonate ions free for organisms to form their shells, for the organisms that require calcium carbonate to make their shells. So here's an example of a phytoplankton that uses calcium carbonate to make its shell. This is a coccolithophore. And so a lot of people around the world are doing research right now to see what are the effects of this ocean acidification on this phytoplankton group. And so far, we have contradictory results, okay? So some people, they will grow these coccolithophores in the lab, and they will change the water in the lab to simulate what would be the effects of ocean acidification. And a lot of people observe this. This is something that has been observed. So you can see here healthy coccolithophores right here. And these are coccolithophores that are grown in slightly acidic water that simulates the climate change conditions, right? The ocean acidification conditions. And you can visually see the difference, right? And they're malformed. However, other studies have shown two things. One, that some of these organisms are able to evolve really fast because the generation time, the time that it takes for this population to double itself allows for so many genetic mutations and natural selection to occur in a really fast rate. So some studies have shown, I think 2 studies have been published showing a year-long or 2-year-long incubation experiments in which you have in the end of the experiment after 1 year or 2 years of this gradual increase in acidification, what you have are some organisms that mutated and had now the capacity to do just fine and go back. So you would have like a phase in which everybody or most everybody is going through this malformation, but then at the end of the day, whomever survives looks normal. Does that make sense? So it's possible for some of these, or at least we think it's possible for some of these organisms to, using the term very loosely here, to adapt, right? To evolve and sometimes adapt. Some of this is built into their genetics and what we call genetic plasticity, and some of it is really evolution, as I mentioned before. So right now, we really don't know what ocean acidification is going to do to phytoplankton. We know, however, it is destroying corals. Corals are being destroyed. They're being killed. I'm not going to go into the details. There are other things that corals are harmed both by warm water and ocean acidification. But I wanted to show an example of a zooplankton here. These are pteropods. It's a type of mollusk, and you can see also how the shells. Can you see the top of the screen, or do you see yourselves in the top of the screen? You don't see yourselves?
No, we can see the top of the screen.
You see the top? Okay, good. So what you see here are pteropods, these mollusks, and they're zooplankton. These are larger than the phytoplankton organisms. They're, they can go from like a few millimeters to a few centimeters in size. But as you can see here, this is what happens when they're exposed to acidic water. So this is definitely work that we are investigating. Again, it's easier to understand the effects on larger organisms than in microscopic organisms. But I got here this piece of information that I thought summarized things pretty well. So one of the expected effects of having more CO2 in the atmosphere, and then therefore more CO2 in the ocean, is that you're going to have more photosynthetic efficiency. Basically, these phytoplankton will have more CO2, and CO2 is what they need to photosynthesize, right? Provided that they have the other nutrients. But this effect is not always seen in the experiments. So available data shows that there is an equally important effect that happens with the respiration in the phytoplankton. So when you lower pH, when you make the ocean more acidic, even though you have more CO2 for phytoplankton to thrive, when you change different, tweak things on the experiments, what you might end up having are organisms that are having a hard time respiring, stabilizing their metabolism, acquiring the other nutrients, even if the other nutrients are in the water, such as iron and zinc. And so really what this field is going towards is what we call multi-stressor effects research. And that's something we're doing in our lab right now, the Mackey lab. We have a postdoc working on these multi-stressor effects. So when you have all these different things changing at the same time, how does the phytoplankton react to that? To change in pH, change in temperature, change in nutrient conditions. There's a lot of research also going on in, as I mentioned before, genetic plasticity and rates of evolution. So the gist of it is that we don't know what ocean acidification will do to phytoplankton yet, but we are actively studying, and it seems like depending on the organism, it can go either way. They can adapt, do just fine, but it might also not be something that you can study in isolation. Does that make sense to you? Okay, so that's ocean acidification. So what about warmer ocean, temperature change in the water of the ocean? Well, in general, what we're seeing, what we're observing is that climate change is triggering shifts of species distribution. So in general, marine species are shifting towards the poles, right? So as the planet becomes warmer, the warmer parts of the planet, which would be near the equator, are becoming relatively warmer too. We're seeing general species kind of shifting towards the poles, and that's leading to change in what we call biogeography. Okay, but the effect on phytoplankton, again, is not completely clear. It's not completely clear. So we've seen a decline in net primary production, a decline in the amount of photosynthesis that these organisms are doing and in their amounts. So net primary production, it's a combination of the amount of phytoplankton and how much photosynthesis they're able to do. So this has been observed. We have observed a decline. And also we have observed some change in distribution. But it seems like different regions, the phytoplankton, different regions respond differently. Okay, so I'm gonna explain some basic principles of why warm temperatures might affect phytoplankton, and then we'll go back to the studies. Is that okay? How are we doing? Okay. So in general, warmer planet. One of the things that we are seeing happen is that there's more ice melting, right? As more ice melts, you're gonna have, near those areas where the ice is melting, you're gonna have less salinity. The water in the ocean is gonna be less salty, right? In those areas. Well, if you have water that is less salty and warmer, what do you think is gonna happen? Is this water gonna tend to be at the surface? Just think of like of air. What happens with hot air? Does hot air rise or sink? Rises. And the same thing goes with water. So the ocean water is normally stratified. Normally, you're gonna find ocean water in general, in most places, you're gonna find the warmer water at the surface, and that water usually it's gonna have a salinity that is, in most cases, relatively less salty than the water underneath it. In general, it's not always the case. In areas where you have a lot of fresher, warmer water, you end up having this very thick layer of water on the top of the ocean. And the greater the difference in salinity and temperature of this top layer, the more stratified the ocean is. You can think of it when you're like, one student once told me that he understood this concept by watching his movie, when this movie was like warming up. Like you can see that like the warmer, frothier stuff is kind of gonna rise to the top, right? And you end up getting these really thick layers. So mixing that liquid becomes harder the warmer the surface part is. Okay, and that's what we call stratification. So why do we care about that, right? Let's see here. For phytoplankton, yeah, got that, Joanna. Okay, now warm water also means less oxygen. I'm not gonna go into this in this presentation because I don't have time, but this is also something that a lot of scientists are studying. is the fact that because the water is warmer, it can hold less oxygen, and that might cause problems for the phytoplankton. So the gist of it is, what do we know? We know that you're going to have global effects, but you're also going to have these regional effects, and the regional effects may be different. And that has to do with this stratification, how much stratification you get in those areas normally, and how much more or less you're going to get with climate change. So this is a picture showing you the same concept of stratification that I just showed you. This is what you usually see when they're trying to explain lakes. So in lakes, you're going to have, again, warmer water at the top, colder water at the bottom, and then the wind will be pushing at the surface, will try to mix things up. If you have a very stratified ocean or a very stratified lake, which is the case here in the summer, right? In the summer, there's more heat. This water here gets warmer, so you have more stratification. The wind won't be able to mix things up very well. When it's winter, for example, the sun is not warming out the water as much because it's dimmer, right? Well, the sun is not dimmer, but the relative position to the sun will make this water less warm. So there's less stratification, so the wind is able to mix things more. Why do we care about this? Would anyone know why do we care about this when it comes to phytoplankton? Need a break, I'm gonna drink water. What is it that phytoplankton need to thrive besides CO2 and sunlight?
Oxygen.
Nutrients.
Nutrients.
Yeah.
Nutrients, yes, nutrients. And if you are away from the coast, those nutrients are gonna be coming, and even in some places, if you are near the coast, these nutrients are gonna be coming from below. Would anyone know here in the coast of California, what do we call that event that brings up all these nutrients from the bottom parts of the ocean to the surface? What do we call it?
Upwelling.
Upwelling. Yes, upwelling is when the wind will blow in a certain direction, and then you have this cold, nutrient-rich, deep water from the ocean come to the surface. And when you have these nutrients come from below to where the light is, the phytoplankton will thrive, right? So that will happen in specific seasons. Usually that happens when you have a relaxation of this stratification. So not in the summer. Usually that will happen, in springtime. That's when you get the spring blooms here in California. And in the fall, you might get a second bloom because that's when you have less stratification. Now, what we're thinking that's going to happen is that because of climate change, the top water, the top layer of ocean water is going to end up becoming much, much warmer. And so what we think that's going to happen is that this layering process, this stratification will become more intensified. The top layer will also be thinner. And that has some other implications. But for us here, what I want to point out to the fact that because this layering is going to be so much more pronounced, and those layers are going to be, you can think of them as, I was going to say, these are going to be much less denser than this water here. Then it's going to be hard for these nutrients to move from the deeper parts of the ocean to the surface. So the nutrients that the phytoplankton will need won't be there in what we call the euphotic zone, the light zone. Okay. Now this picture also talks about carbonate solubility. I'm not going to go into this today, but if you want to ask me about this later, we can talk about that too. That has to do with the ocean acidification that we were talking about earlier. Okay. All right. So that's the stratification. So what do we make out of all that? Well, right now there's a lack of consensus of how climate change will affect, not just how it will affect, or how it's affecting phytoplankton production. Okay. If we look at the data from satellites and combine that with long-term field observations, some scientists have shown using those methods that phytoplankton in the Pacific Ocean, the production, the amount of phytoplankton and the photosynthesis will be changing depending on large-scale climate patterns, such as El Nino. So that, that will create some fluctuation that will be happening as noise behind the climate change signal. They also show that chlorophyll concentrations are going to be typically lower during warm periods. So that's what these guys here, this researcher and his colleagues published. And then this other guy, Boyce et al., 2010, published this big bombastic paper. They used a combination of this data with some water transparency and chlorophyll measurements, and then they extended the historical data set using these proxy records that they had, and they then came up with this conclusion that chlorophyll concentration decreased in large parts of both the North Pacific and the North Atlantic. And then they showed that that was correlated, that was paralleled with increases in temperature. This paper was big. It was like a big paper. Everybody was talking about this paper because they were the first ones to show that global warming was decreasing the amount of phytoplankton in the ocean, okay? Now, that's the beauty of the scientific method, is that once somebody published something like this, you have 50 people now trying to prove this person wrong. So that generated a number of other research papers, and I'm gonna summarize the findings. There's a lot of text here, but I'll walk you through, and again, interrupt me if you want. All right, so we already established that more stratification equals less nutrients. Are we all okay with that? Okay. So we're also expecting that predators, grazers, zooplankton will be more stimulated in warmer water. So apparently the increase in temperature in the ocean water, scientists don't think is going to affect the phytoplankton itself, the metabolic process of the phytoplankton. They don't think that the warmer water is going to make them more or less efficient. But they think that what's going to happen is that the grazers will be reproducing more, and they will be more active. Okay, and so compared to photosynthesis rates, the metabolism of those heterotrophic organisms, those are the zooplankton, they will be more sensitive to temperature. So they're expecting the warming will increase consumption. The grazers, the zooplankton, they'll be eating more phytoplankton. And that could strengthen what we call the top-down control, meaning more grazers will be eating the phytoplankton. And that will, besides the stratification that we already talked about, so the phytoplankton will be, it's kind of a double whammy. They're gonna have less nutrients, and on top of that, the zooplankton will be eating, there'll be more zooplankton to eat them. How's that? Is that bad news enough? Okay, here we go. But some other studies have found increase in productivity in other areas. So that would be the case of the Pacific and the Atlantic Oceans. In those two areas, they showed an increase in productivity, increase in phytoplankton. Again, related to that, those changes in stratification, because not all the places on the planet are under the same regimen for stratification. Simulation studies, they've shown that some of these metabolic rates might overcome the temperature. So again, I'm showing all this to show you how, what the controversy is. I already talked about this, how the grazers will be eating more. Okay. Now, I wanted to share this with you because it's pretty new research. So these people here published this paper just last year, okay? And these are people from Woods Hole. Now, they were studying just the North Atlantic. In the North Atlantic, and they use a really complicated method. Instead of using chlorophyll data or satellite data, they actually use trace gases that are normally released by phytoplankton, and that gets trapped in ice cores. And their research shows a steady decline of phytoplankton over the years since the Industrial Revolution, that's correlated with change in temperature. And here we have it. So for them, according to their study, in the North Atlantic, we're looking at 10% decrease in phytoplankton productivity for that region since the start of the industrial era. Okay, they showed the correlation with surface temperatures over time. And here's why I selected this to show you how complex this can be. So their research, the one thing that they connected that decline in phytoplankton, 10% decline in productivity for that region, is not just the warmer water, stratification and the grazers as we talked about, but also they correlated with change in what we call, in this current here, that we call the Atlantic Meridional Overturning Circulation. For short, we call it AMOC. AMOC is this war, you guys see my map? Yes? Would anyone know the name? So do you see my pointer? Where's my pointer right now?
Caribbean.
Caribbean, Gulf of Mexico right here, right? So you have this warm water that travels in the Atlantic Ocean. So this is the east coast of the United States right here. And this warm water comes, it brings warm water from the equator, and it travels across the Atlantic all the way to Europe right here. What's happening right now is what's melting because of global warming. We see the visual of that all the time. Which country is melting really fast? Greenland, all the way up here, okay? As Greenland melts, this fresh water is going on the surface of this ocean area here. Now, think with me. We talked about this. Fresher water, warmer planet. What is going to happen with the stratification in this area? Is it going to increase or decrease? Increase. Increase. So now you have more stratification. This water cannot sink. It goes both ways. If you have more stratification, not only water cannot go up, but it cannot go down. This is what we call this the slowing down of the amok. Okay, the amok is getting sluggish. It's sinking less water. It's not mixing this deep ocean surface water. And as you can see, this is all connected. This is what we call the ocean conveyor belt. All these major ocean currents, they connect and they are mixing nutrients. The blue lines that you see here are the deep currents, rich in nutrients, cold water. That water travels around the planet. And when you see that blue line becoming orange, what's happening here? What is this? My pointer is in what kind of process is happening? Actually, I'm gonna go home. Oh, we don't see, oh, here. This is California right here, somewhere here. What is happening here? What is this transition zone here called? When water comes from, you already told me the answer earlier.
Upwelling.
Upwelling. Upwelling. So now what we have is upwelling and downwelling becoming really sluggish because you have more stratification. You don't have that mix of nutrients happening. So again, we'll go back to that issue that we talked about. Some regions might be seeing an increase in productivity while other regions are seeing a decrease in productivity. It's maddening, isn't it? Yeah, but the good thing is that you have people, and people who like to study this stuff. And then what they do is they combine all this knowledge about what's being observed, and they create these models to try to figure out what is the net result globally, okay? And then by creating these models and by overlaying that with the climate models, they come up with these forecasts. So now I'm gonna show you what based on these processes, this metabolic responses, grazer responses, nutrient deficits, and nutrient increases in different regions, all this is put together, combined in these models. So there's this recent paper. I can send you all these papers if you ever want to see them. This group here published their own model results, and they reviewed a bunch of them just last year. So this is what they expected, okay? I'm gonna walk you through. So numerical models, as I said, they provide a means to explore potential future change, blah, blah, blah. Okay, so remember, we're looking at scenarios, right? We don't know exactly what's gonna happen. So these people here, they just said, okay, what if things continue as they are? Remember I said that they call business as usual. And we see an increase of 3 degrees Celsius, but from now to the year 2100. So these are their assumptions, okay? What will happen with the phytoplankton? When they run these models, in general, what they see is a moderate decrease in the globally integrated primary productivity. So when you look at all these different regions and all these different processes, less nutrients due to stratification in some areas, sluggish ocean currents, sluggish upwelling, sluggish downwelling in other areas, grazer effect in oxygen, which we didn't talk, but it's in here too. Okay, when you see all these different forcings on phytoplankton, they come up with this conclusion, and not only one group, several groups of modelers have concluded that what we would see is a moderate decrease in primary production. driven mainly by those macronutrients that we talked about, okay? Although some increase might be seen in some regions. Now, my people, oh, no, there's more. Okay, so the meridional overturning circulation, remember the AMOC, continues to slow down because of the melting of Greenland, becomes more shallow relatively to current day conditions. So regionally, you're gonna have that. You have a reduction in the supply of micronutrients all over the planet. Sea ice retreats. So in many regions, there's a decrease in productivity, decrease in phytoplankton because of that macronutrient supply reduction. In polar regions, the reduction in sea ice leads to greater productivity. Why? Because now you have more area for the phytoplankton. You have more sunlight reaching the surface of the ocean. We're seeing an increase in these models of phytoplankton in polar regions. While in the rest of the planet, mid to high latitudes, probably not lower latitudes, but mid to high latitudes where we are here, you're gonna have complex combinations. Some places you're gonna have increase, some places you're gonna have decrease. Okay? This is not considering any kind of input of nutrients from runoff, by the way, okay? And this is also not considering any impact of overfishing. Just caveats here for you. All right, I'm not gonna go through this because I know you're all tired, I am. You can look at this later if there's something here that you wanted me to talk, but it's related to that initial slide there about size. So we think everything's gonna get smaller in general. All right, so my professors here at UCI, they decided, you know what, 2100 is not far enough into the future. Let's take these models and push them into the year 2300. Let's see what happens then. So they did that, and in 2018, they published this paper. And they said, okay, you know what, as climate continues to warm, now you're gonna have winds changing. Winds are not, well, they will be changing into the year 2100, but as you move forward, winds are gonna be changing so much that now you're gonna have even more change in the ocean, and with more change in stratification and nutrient supply. Sea ice will have disappeared, right? And so what they concluded, I'm just gonna take you all the way down to the conclusion here, is that by the year 2300, you would see declines in phytoplankton that would lead to declines in fisheries of more than 20% globally and 60% just in the North Atlantic. Now, some people will shrug and say, hey, we might not even be around here in 2300, considering how bad things are right now. I'm probably one of those people that went like, it's too far off in the future. We're kind of dealing with survival here. And I understand that, but the beauty of these models is that by projecting really, really far off in the future, you can figure out which knobs are more important in certain regions, okay? And so what they're showing is that when you look at global productivity of phytoplankton, by projecting way, way, way into the future, what they're showing is that the Southern Ocean is really important. The Southern Ocean is really important. Today, it plays a key role in the transport of nutrients to lower latitudes, to the equator. And then by projecting it so far into the future, these models have taught us that this change as a result of climate change. These supplies of nutrients that I showed you in this global conveyor belt are so delicate through all these currents that connect, that when climate change will be changing not only these very obvious things like stratification, grazers, but it will also be changing the way these currents connect to each other and where they sit in different depths of the ocean. So this picture here summarizes that. It shows you, I'm not going to go through all of it, but it shows you how, according to these studies, there's going to be more nutrient trapped in the Southern Ocean because of climate change, because of the change in the winds caused by climate change. Okay, I think that's the last thing I had. I didn't have a summary slide, but maybe we can do that together. I know you're probably as exhausted as I am, but if you have any energy left, do you want to summarize this with me? What do we know? Do we know what's going to happen to phytoplankton because of climate change? exactly. We don't know exactly, but do we have an idea?
Yep.
What are scientists telling us that they think is going to happen? First, is it going to be the same all over the planet?
The impacts of climate change will be different depending on the region.
Right.
There'll be global impacts and there will be regional impacts.
Perfect. That's right. And then when we put all these regional impacts together, it seems based on these calculations that we have right now, that we're going to have a slight or moderate decline in productivity globally, average, for the whole planet, all the way down to 2100. So it shouldn't be something like that we're going to be super concerned right now, and considering the other things that we are very, very concerned about in terms of climate change impacts. But as we move forward in time, we understand better how there's some stuff that we won't be able to fix. I think that's the main point, is that there's some stuff that if we just allow to continue getting bad, even though the impacts on phytoplankton are not immediate, later on, they're not fixable. If that makes any sense to you. Because the ocean has this really long time memory. So the things we're doing to the ocean now will take hundreds to thousands of years to manifest itself. But when they do, there's, how are you going to stop these major ocean currents? Does that make sense? So it's different from like species going extinct right now on land because the temperature is too warm for them. Or even in the ocean, there are some species in the ocean that are just can't deal with the warm water, like kelp, for example. But phytoplankton seems like they're gonna be okay for a while. Cool. I did not talk about harmful algal blooms at all, right? We did have that conversation a few weeks ago, but we can definitely, I'll send more information on that, just because it was such a long presentation. All right, so now I'm gonna open for any questions or comments you might have. I'm gonna close this.
Joana, before you close, can you go back to the previous slide?
I can, yes. Here we go, right there.
No.
No.
One more back.
Okay.
It was the reduction in fisheries.
Oh, yeah. So
Farther
that's,
back.
right, hold on. Let me close this. So that's the conclusion from my professor's study here. Yes. So this is projecting up. This is this, right?
That's it.
Yeah.
That's it. This is by 2300, which is like how many years in the future? 280?
Right.
The fisheries yields will be reduced by 20%. But what I have seen is that commercial fisheries the fish are going to be fished out by 2045.
Exactly. So that's what I'm saying. None of these models take into account overfishing. None of these models are taking into account runoff. Okay. None of these models are taking into account chemical waste that might actually be causing sediment loading that causes shading in amazing areas. My own research is looking at the effects of fossil fuels and iron from fossil fuel emissions from ships on the ocean. There's all these other different caveats that are not being taken into account in these models, Luke. So yeah, like this is a prediction purely theoretical, not taking into consideration that there might not even be any fish by then anymore.
Thank you.
Good point.
And Joana and Luke,
yes.
Another factor going in the same direction as Lou's observation is the warming of the water, which you mentioned, Joana, briefly, changing oxygenation levels, which would also go in have the same directional impact on all layers of the oceanic ecosystems above the phytoplankton,
right,
driving down fish and
yes,
zooplankton.
Yes, and there are some interesting studies. Of course, I didn't have time. I would not be able to cover that all in one presentation, but there's some really interesting studies showing how fish are already migrating poleward. So that was like that one general information, like I just mentioned that in general, whomever can swim is moving away, not just from warmer water, but from those low oxygen areas. So those low oxygen areas are already forming in the ocean. And we're seeing whomever can swim fast enough moving away from those low oxygen zones. So you're gonna have, so you might have a lot of phytoplankton in the place where there's nobody to eat the phytoplankton, and you get these blooms that go out of control, and then it just become, eutrophication. But eutrophication, usually we think of it like near port or near marine or near bay, and now you're gonna have eutrophication like random open ocean areas. Does that make sense to you all? It's like, yeah. So if anyone is interested in studying this, there's lots of room. There are a lot of questions to be answered. But I think the exciting part here, for me at least, is how this all connects with climate. Of course, again, I couldn't put that in one presentation, but phytoplankton are part of what we call the biological pump. Again, not for our time period, not in a matter of 100 years, but in long terms, there's this feedback that happens in the planet that, allows for these balances to be reached. Whether we humans are gonna be able to survive, then that's another different question. Whether a lot of other species that we are killing, really, whether they matter or not, then that's another debate. But in terms of these processes that will be moving carbon from the atmosphere into the ocean, from the ocean into the sediment, that eventually becomes the fossil fuel that we're burning in reserves of carbon, that to me is fascinating as a scientist. As a climate activist, not so much, but as a scientist, it's pretty interesting. Let me close this actually so that I can see all of you and you guys can see each other. Hold on, how do I do this again? It's this here, and I stop sharing. All right, who's standing? Who do I have standing? Who's still alive? Nancy, did you just join right now? Because you look refreshed. I think you just joined us.
Joanna, could I say something?
Yes.
This would be a fascinating thing to add to the tours at Amigos de Bolsa Chica that they have before COVID-19 as a station. We have stations for the birds, we have stations for the ecology. Bringing this home would be a great way to educate the public, I think. And even beyond that, I was thinking, I remember reading something in the Turn Tide or something that was just published on the different signs that have been added to the reserve. And I haven't seen any signs about the impact of climate change, but I may be mistaken. And someone can correct me if I'm incorrect. But I would just bring it, going from a global position to a local position. This is just fascinating to me that if we could bring this to the public, that this is a tremendous opportunity to educate the public about climate change, the impact on phytoplankton, and then specifically, this would lead to other areas of research, what's happening to the reserve because of climate change. I think that would be a fascinating area, and that could be even a future talk that you could do if you want to, or others.
I think that's an excellent point. Yes, I'd love to see more focus on climate change in everything that we do, considering how urgent the matter is. I would think that specifically, like you guys said, I would not give this presentation to a general audience, right? I'm giving this presentation to you all because you're interested in phytoplankton. You're people that I already knew had the capacity to follow all this. I mean, this is a lot of information. It's definitely something that happened with the phytoplankton because of climate change. But that being said, I think that your overall point is amazing and very important. And yes, we should do exactly what you said. It's to talk about climate change in the context of what we do. And there are many measurable impacts of climate change on wetlands, for sure. There's much less uncertainty on the impacts of climate change on wetlands than on phytoplankton. So we can definitely create materials that that will be based on what we call consensus. Because as you can see, there's no consensus in the phytoplankton community yet regarding the effects of climate change on phytoplankton. But there's plenty of consensus in other fields. So we should definitely be thinking about that. Would anyone volunteer to be the head of a committee? To include more climate change in everything we do, including signage and education materials? Who wants to raise their hand? Ha ha ha. We'll sleep on it.
Well, Joanna, I want to echo the comments that you just made about consensus in the scientific community, and address the politics of education about climate change. It is almost a dangerous thing for the scientific community to go high profile with the more controversial aspects of science in this area, because our opponents are always very quick to seize upon any perceived weakness in the consensus of the scientific and environmental communities, and can twist arguments and scientific evidence very, very effectively to their own benefit and to the detriment of the environment. And so my own suggestion strongly is that when we communicate about climate change, we do so with those points of evidence that are the most crystal clear.
Absolutely.
Like the increase in acidification of ocean water, which is absolutely scientifically unarguable. Yep. The increase in temperature followed by decrease in oxygenation levels. Those are some points where there's almost no possible way.
Right.
For opponents to twist the science.
Absolutely. Absolutely. So, the presentation like today's was really made for people who are interested in phytoplankton, right? It's not something that is meant for like general education. And just echo what Vic said. If anything from a presentation like today's that we can convert into a good message for the general public is this one. And that's one that I used to share with my students in the community colleges. Look at how complex it is, or how difficult it is for a scientist to prove that they are right. It's not easy. The scientific process, the peer review process, it takes years for you to be able to convince most of your colleagues, people that you're going to have lunch with, people who are your friends, they share the same interest that you do, and yet to convince them that what you published is really the explanation or the interpretation for reality. It's really hard. So when you hear about a group of scientists that have consensus about something, that means that that was achieved with a lot of tears, sweat, and blood. The process of the scientific consensus, it takes a lot of time, a lot of money, a lot of people, a lot of brains, and that's why it's reliable. When you hear that 97% of the scientists that published on climate, on issues related to climate, agree that climate change is real, that it's really problematic, and that it's caused by fossil fuels, that means a lot. Having consensus in the scientific community means a lot. So I think that's what we can take away, if anything, from a presentation like this for the general public, is that look how difficult